Hello, folks. How are you? I hope things are going well. We are now moving into Lecture 8. We will start with a review of Lecture 7, just like always. We will be doing a lot of three-dimensional images in Lecture 8. Most of what I'm going to be presenting to you is what these things look like. I'll show you the table that's available. You will have that table available on the test. In all likelihood, what you will see on an exam is you're either asked to draw the Lewis structure and then determine what the molecular or electronic geometry is for these things, and we'll get to those terms in a couple of minutes. Or you're going to be presented with one of these structures and asked what its name is. So you'll need to be able to use the table to determine what those things are. And I'll talk to you about how we do all of that. So again, if you have any questions, comments, problems, please let me know. Try to reference the lecture number, the approximate time in the lecture, and your question, and I'll do the best that I can to answer those. Okay, thanks. So, review from last time. What's an ionic bond? Well, an ionic bond is something where we have transferred electrons between usually a metal and a nonmetal. So we have an unequal sharing of electrons. One has been transferred completely from the metal to the non-metal. In a covalent bond, on the other hand, we have some sort of sharing of electrons. A perfectly covalent bond means that we're sharing equally between the two partners. This is like co-parenting happily with a child, where you're spending half of your time in one with each parent. That is a covalent bond. If it's listed as a polar covalent bond, we are sharing electrons, but not evenly so. So we talk about like oxygen having a greater pull for electrons than hydrogen does, and therefore that oxygen-hydrogen bond being a polar bond, with the electrons falling more towards the oxygen side. So consider formaldehyde, H2CO. So draw the Lewis structure. Well, let's draw a Lewis structure for H2CO. H2CO. Carbon's going to be in the center for this one. You know that hydrogen gives me one electron. I have two of them, so it's 2 electrons from hydrogen. Carbon gives me 4 electrons in the valence. There's one of them. Oxygen gives me 6 electrons. There's one of those. And so that gives me 12 electrons total. I'm going to have my carbon in the center. I'm going to put my oxygen up here, a hydrogen here, and a hydrogen here. Draw one bond in between all of those, which gives me 2, 4, 6 that are taken up. So we have 6 electrons left. Now, my hydrogens are already full. We don't need to fulfill their octets because they don't get an octet, they get a duet. So we're going to talk about the oxygen. It needs 6 electrons to make an octet. So 1, 2, 3, 4, 5, 6. Okay, that takes all my electrons. Awesome. So everything is taken care of, right? Not so much. Carbon doesn't have a full octet. So how can we take care of that? Well, we can take one of these non-bonding pairs that we have on the oxygen and move that into a double bond between carbon and oxygen. Now, if I do that, does that change anything? Well, okay, let's talk about this. So what are our formal charges here? Hydrogens are going to be the same. So we have 2 normally minus half of the bonding pair. So that gives me, 1 electron normally minus half of the bonding pair, which means that my formal charge for the hydrogen is 0. Carbon normally has 4 electrons, and that's such a mess, oh my lord. Can anybody read that? So 1 electron minus half of the bond that's there gives me 0. Carbon normally has 4. We subtract half of the bonds. So 2, 4, 6, 8. And that gives me 0 there. Oxygen should have 6. I subtract half of the 2, 4 minus the 2, 4 for the lone pairs, and that gives me 0 on that as well. So I have no formal charge on this. Everybody who can have an octet has an octet. Everybody who wants a duet has a duet. So that's my structure that we're talking about there. Formaldehyde has that particular structure. Awesome. Next question. What is the total number of electrons in this molecule? We talked about that, right? Total number of electrons that we had was 12. All right. Are there any lone pairs on the central atom? No, I have no lone pairs on the central because we didn't have any electrons left to give to it. Assign formal charges to each atom. We did that. Hydrogen is 0, carbon is 0, oxygen is 0. Are there any resonance structures for this molecule? No, because they don't have a double bond that's going to move anywhere. All right, it's always going to be between the oxygen and the hydrogen and the carbon. There's only one such thing that we can have. Is that a polar molecule? Oh Lord, is this polar? Yes, actually it is, because oxygen is more electronegative than carbon, and I have a higher electron density on the oxygen than I do on the carbon. So I'm pulling electrons towards this end of that molecule, so it is a polar molecule. Questions, comments, problems on any of that? Okay, sweetness. Awesome. Let's see what we can do next. So now let's move into our new material for this lecture. VSEPR. Valence shell electron pair repulsion. So the valence shell is that outermost electron-occupied shell of the atom. It contains the electrons that are usually involved in the bonding. Double and triple bonds are considered the same as a single bond. They do take up more space than we consider them as if they do not. There are 2 or more resonance structures. You can use any of them to determine the geometry. The formal charges are not shown. Okay. Now, VSEPR is used to determine molecular geometry. We'll get to those in just a few minutes. So to determine the geometry of a molecule, we need to be able to answer 2 questions. How many bonds are on the central atom, and how many lone pairs are on the central atom? So that's what we're going to be concerned with. The only way that I know that is to be able to draw a Lewis structure and to make sure that it is the Lewis structure that is the most stable for that particular molecule. That's where the last lecture comes into what we're talking about now. All right, let's see what we can do. Questions, comments, problems on VSEPR and how it's defined? Hope not, but if there are, let me know. Molecular geometry. Okay, this table is sideways, so it's a little awkward to look at, but hopefully you can flip your printouts or turn this in Adobe to look at it. This talks about electron groups, bonding groups, lone pairs. Electron geometry, molecular geometry, and approximate bond angles, and then gives you some examples. So it shows you a Lewis structure example, and then what we call a space-filling model example. So we're going to talk about what all of these things are, but let's do that in context of looking at some examples. So let's go ahead and talk about this next one. What we're going to do, excuse me, I'm sorry. What we're going to do is look at an example of all of these to see what they look like, okay? So we'll talk about where these things fall and how we determine which one of these it fits into. So let's see what comes next. What the heck do I do with that? The rules for molecular geometry are simple. Draw the Lewis structure. Determine the number of bonds on the central atom. Determine the number of non-bonding pairs, i.e. lone pairs, on the central atom. Look at the table to determine what the name of the structure is, and let's practice. So, electron versus molecular geometry. These are those first 2 columns in the table that I showed you. The electron geometry, the electron configuration, takes into account all sets of electrons around the central atom. This determines the shape the electrons take around the central atom. It's also considered the parent structure for the geometry. We call that electron geometry, e.g. Molecular geometry, in this case, only the molecules, the atoms that are there, are considered to describe the structure. So this basically ignores anything that is a lone pair or non-bonding pair. But because those non-bonding pairs affect where it sits in three-dimensional space, then we have to talk about how that affects what we're looking at. So once you have the electron geometry, then look to see how many of the sets of electrons are lone pairs. The number of lone pairs will determine the molecular geometry, and that's called the molecular geometry, Mg. Okay, so electron geometry takes everything into account and lists the parent structure. Molecular geometry takes into account only the things that are actual bonds, but that name is influenced by all of those other lone pairs that we aren't talking about. All right. Bear with me just a second. Notice something I need to fix. So, questions, comments, problems, any of that? Hopefully not. Let's see what we're talking about. So we're going to talk about linear. This is an electron geometry of linear, molecular geometry linear. Okay. Number of electron groups is 2. Number of bonding groups is 2. Number of lone pairs is 0. The approximate bond angles are 180 degrees. So this is a structure. CO2 is considered a linear structure. It has 2 sets of electron groups. 1, 2. 1 on each side of the carbon. There are no lone pairs associated with this, and therefore, in order to get them as far apart as possible, there needs to be 180 degrees between them. Now, this is a space, and these are 2 different ways to draw the same thing. This shows the Lewis structure, with all the electrons explicitly shown. This does not. Okay, so this is just the bonds that we would talk about there. So that's a linear structure. 2 electron groups, 2 bonding groups, no lone pairs. Okay, awesomeness. Trigonal planar. Again, the electron geometry is trigonal planar. Molecular geometry here is trigonal planar. There are 3 electron groups, 3 bonding groups, 0 lone pairs. So the approximate bond angle is 120 degrees. This is all flat in one plane. I have 3 things connected to the boron. Remember, there's only 2, 4, 6 around that boron because we talked about this before. So 3 bonding pairs, no lone pairs, trigonal planar. 120 degrees separate these bonds in 3-dimensional space. So that's trigonal planar. Now, what if these aren't all molecules? What if one of those is a lone pair? Well, that's where we get into the next structure. And that's going to be bent. So instead of having those 3 molecules that we talked about in the last structure, it's still an electron geometry of trigonal planar. 3 sets of electrons around that central atom, but only 2 of them are considered when we talk about the molecular geometry. Because there are 3 sets of electrons, this one set up here that's not explicitly shown here, but is shown right there, that affects the bond angle that you see. So these the 2 atoms that are in the molecular geometry that are connected to the central atom have a bond angle of less than 120 degrees. This lone pair takes up more space than a bonding pair would, and therefore it shrinks the bond between the 2 oxygens that are there. This is called bent, all right? Because the structure that we look at when we don't see those electrons that are up here is bent, okay? Awesome. So that's 3 electron groups, 2 bonding pairs, 1 lone pair. Awesome. What's next? 4 electron groups. This base structure is called a tetrahedral structure. So again, the electron groups are tetrahedral. When we have all 4 of them explicitly shown with 4 atoms, that's a tetrahedral molecule. It's 4 electron groups, 4 bonding groups, no lone pairs. The approximate bond angles are 109.5 degrees. Now notice that this is not your typical, it doesn't look like this. It's not 1, 2, 3, 4 in a flat plane. We actually have this in 3 dimensions. So we have this trigonal thing down at the bottom and one thing sticking up out of the top. All right. Molecular models can help you to visualize this. For me, without those models, I couldn't make sense of any of it. All right. So what you should be doing in lab is to be building these structures so that you can see what they look like. If you can't do that, then finding a molecular model kit that you can build with is extremely helpful. But it's not necessary unless you absolutely think you need it. Now, I'm going to tell you right now, if you're going to take organic chemistry, you would benefit from having one, because you're going to be able to use it much more in organic chemistry to help you understand those structures. Okay, so this is the structure we're talking about. Those bond angles are approximately 109.5. We have 4 electron groups, 4 bonding groups, and that's a tetrahedral molecule. Let's take off one of those bonding groups and make it a non-bonding pair. If we do that, then our structure is trigonal pyramidal. So we still have that pyramid down at the bottom, but now one of them is that straight up electron pair is a lone pair. So we have 4 electron groups total, 3 bonding groups, and 1 lone pair. Your approximate bond angles are going to be slightly smaller than they were before. So it's going to be less than 109. All right. So your electron geometry is still tetrahedral, but the molecular geometry is trigonal pyramidal. Okay. So trigonal pyramidal, 1 lone pair, 3 bonding pairs. All right. And NH3 has this particular structure. Here you can see the lone pair and the 3 bonding pairs, and that gives you the structure that you're looking at. And this doesn't look the way I would have expected it to, but that's okay. We can go with it anyway. All right. Now if we go with 4 electron groups, our electron group is still listed as tetrahedral. 2 bonding groups, 2 lone pairs. This molecular geometry is bent. So again, we have 2 of these that are bonding pairs. We still have 2 sets of non-bonding pairs that are up here. So this thing is bent. All right. 2 sets of non-bonding pairs, 2 lone pairs. That means that this is bent. Okay. Woo, 5 electron groups. Now your base structure is called trigonal bipyramidal. So again, we have 3 things in the plane. So that's our plane. But it's bipyramidal because there's stuff above that and below that. So it's trigonal bipyramidal. 3 things in the plane, up and down. That's trigonal bipyramidal. It comes from 5 electron groups, in this case, all of them being bonding groups. So the electron geometry and the molecular geometry are listed as the same. That makes them both trigonal bipyramidal. The bond angles in the equatorial zone are 120 degrees. The bond angle between that plane and the one above is 90 degrees. That plane and the one below is 90 degrees. So those are our bond angles, 120 and 90. We have 1, 2, 3, 4, 5. PF5, this is the one we talked about before. There are no lone pairs on the phosphorus. There are 5 bonding pairs to the fluorines. And that's a trigonal bipyramidal. If we take one of those bonding pairs away and make that a lone pair, that's going to happen in the plane. Now, it happens in the plane because that's where we have the most space to put it. Now, that does mean that we've affected those geometries slightly. So the one in the plane is going to be less than 120 degrees, and the ones out of the plane, they're going to move slightly away from that lone pair to make them less than 90. Okay. If we talk about what that structure actually looks like in 3 dimensions, that is called a seesaw. So its electron geometry is trigonal bipyramidal, but because there is 1 lone pair, the molecular geometry is called seesaw. Okay? 5 electron groups, so our electron group is still trigonal bipyramidal, 3 bonding groups, 2 lone pairs. We have something that's called T-shape. And what happens is that 2 of the sets in the equator plane are replaced with lone pairs. So the bond that exists between all of those things is less than 90 degrees. We end up with something that has the one that was above, the one that was below, and the one that is in the plane. It looks like a T. All right, so T-shaped. That's for 3 bonding pairs, 2 lone pairs in a trigonal bipyramidal electron group structure. Okay? Trigonal bipyramidal, where we have 2 bonding groups and 3 lone pairs, is going to be linear. So all 3 in the plane are lone pairs. That leaves us with 1 up and 1 down. That's a linear structure. Right? Bond angle there is going to be 180 degrees. So linear again from a different structure. Bent occurs off of a couple of different structures too. All right. Octahedral. So there's 6 electron groups on this, SF6. So all of these are bonding pairs. There's no lone pairs. There's 6 of them. So 6 bonding pairs, 6 electron groups, no lone pairs is octahedral. Approximate bond angles are 90 degrees, right? So instead of having 3 in the equatorial plane, we have 4. And all bonds are approximately 90 degrees. Okay, awesome. We're getting so close. If I take one of those bonding pairs off and make it a lone pair, then I have a structure that's called square pyramidal. Now, since it's 6 electron groups, it's still an octahedral electron geometry, but it's a square pyramidal molecular geometry. Okay? What happens is that one of the lone pairs goes into this plane. So we have 3 things in the plane, 1 above and 1 below. So XeOF4 is one of these particular things. Remember, this multiple bond, the double bond, is considered as just one electron pair that we need to deal with. It's not really exactly true, but it's a very good approximation. Each of these bonds is slightly less than 8 degrees. Excuse me, because of the presence of the lone pair. All right, so that's what we're talking about for that one. Now, what happens if I go from an octahedral with 5 bonding groups and 1 lone pair to an octahedral with 4 bonding groups and 2 lone pairs? Well, that's this. It's called square planar. So the electron geometry is still octahedral, but the molecular geometry is square planar. What happens is that the lone pairs, in order to be as far apart as possible, go up and down. So they're 180 degrees from each other. And that means that the other 4 have to be in the plane. Those 4 are going to have approximate bond angles of 90 degrees. So that's what we're talking about for that. XeF4 is one of these structures. Okay? Dun, dun. Questions? Comments? Problems? No, I hope not. That is actually how we do that. And that's it. Now, remember, the way that you would see this on a test, you can have something where they tell you, draw this particular structure, decide what the molecular geometry is, decide what the electron geometry is, all of that good stuff. And how would you do that? Now that we've looked at all of these things, the electron groups tells you how many in total there are. So it's the sum of the bonding in the lone pairs. So the electron geometry is going to be what you determine based on that number. Electron groups determines electron geometry. The bonding groups determines your molecular geometry. And then your bond angles are determined by the angles from the electron geometry and then the modifications from the molecular geometry. Okay? Now, all of these structures were shown to you before, but that's what we're going to have for that. All right. Now, this takes everything into account. The book that you're using actually splits this into 2 tables. So the one that describes where you have no lone pairs, and then the one where you have modifications from those to include lone pairs. I don't do it that way. I always do it based on what is the number of electron groups Do that first. That determines which base structure you're talking about. And then determine how many lone pairs you have. And that determines what your molecular geometry is. Okay? So that's how we deal with that. You may be asked to provide an example of one of these things. You should be able to do that. You may be asked to draw a Lewis structure and then determine what the molecular geometry is. You may be shown a picture of a molecular geometry, asked what its name is. And again, you will have this table, so you should be able to manage that. Okay? Questions, comments, problems on any of that? I hope not. That brings us to the end of our materials for Lecture 8. So that's all of our happy drawing. That's everything I have for this. Let me know if you have any questions, comments, problems, anything, and I will see you next time. Thanks, guys.